Hi, this is Barrett Givens, and in this video, I want to talk about two simple facts about bases. So we have a definition of a basis, but oftentimes we'll find that when we're trying to look at the two parts to the definition of the basis, we will find that actually the second part, it turns out there's kind of a simplification. It doesn't happen for every basis, but it does for some. And so when you're trying to show that something is a basis, if you're able to show this, then it can simplify your arguments a little bit. Okay, so the lemma says, suppose you have a collection of subsets of X such that for all little a and capital X, there exists a capital B in the alleged basis that A is in B. So that's the coverage part of the definition of a basis. And then the second statement here is, let's say that we have, whenever you take two sets in the basis, their intersection is also in the basis. Then I claim that B is a basis. I'm calling it a basis even before I've shown that it is a basis, so I should be careful about that. Okay, let's just compare to the definition of basis. The definition of basis, the one part is the same, right? That's the same as in the definition of a basis. The second part says for all B1 and B2 in fancy B, for all C in B1 intersect B2, uh, there exists a B3 in fancy B such that C is in B3, which is a subset of B1 intersect B2. And now that I'm looking at this lemma, I think I want to just make one little edit to it. I'm going to say whenever B1 intersect B2 is not empty. If it's empty, it's not in the basis. So we're assuming it's non-empty. Okay, so in the maroon over here, I have the definition of a basis, and then in the blue, I have something else. Okay, they're not equivalent, but if the number two from the lemma is true, then the number two from the definition of the basis is true. Because if number two from the lemma is true, then when you're looking at the definition of a basis, you could just let the B3 equal the intersection. Okay, so for some possible bases that you might look at, you might be able to prove this second statement from the lemma, and that's a little easier to prove than the actual definition. And what this lemma says is that if you can prove this second statement from the lemma, that that's sufficient, okay? That tells you you have a basis. Now, not every basis satisfies this. So if B1 intersect B2 is not in B, that doesn't mean you don't have a basis. It means you have to go back to the regular definition of basis. Okay. Secondly, when you have a basis, we know that whenever we intersect two sets and we have a point in their intersection, then we can find, another set that has this nice property. But in fact, if you have a basis, then whenever you have a finite number of sets in the basis, B1, B2 up to BK, K could be any finite number, and you intersect all of them, then there is another set, which I've called capital C here, such that little c is in capital C, contained in the intersection of all the basis sets. So when I take a collection of basis sets that looks like, some collection like this, and I look at a point in their their intersection, so here's the intersection, and I take a point in here, C, I can find a new set, which I've called capital C here, that's contained in the intersection and that is contained, that contains the point C. And that's just basically an inductive argument. Like we know it's true for two. So what you would do is you would find a B3 prime inside of B1 intersect B2. And then you would take that B3 prime and intersect it with B3 and get a B4 prime and so on. You would just sort of do them two by two by two, going down, 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 down until you get the set that you want. Okay, so those are just two nice facts to know about bases that will simplify arguments for us later. So thank you so much for listening.